Okay. Good. Thank you, everybody, for coming. Actually, like you can see in the title, there are a lot of buzzwords, a lot of technologies. So my presentation is quite packed, so I have to be fast to finish in time. So I jump directly into a short introduction. So my name is Volker, and I'm a software developer, team lead software developer, actually, for InnoGames. And you can find me on Twitter, LinkedIn, Xing, whatever you like. And actually, I'm leading a team of data engineers, and we are dealing with the whole data infrastructure at InnoGames. And shortly about InnoGames, so we are an online gaming company, and we have more than 160 million players all around the world, and more than 400 people working for InnoGames from 30 different countries. And the main office is in Hamburg, but we also have the office in Düsseldorf. Well, and the first thing I want to do is I want to tell you a little secret. So the secret about how to create a successful company with free-to-play online games. So InnoGames is a successful company in that direction. So I want to tell you the whole secret about it. And it's fairly simple. So first of all, you develop an awesome game. Then you get some users. Then you sell virtual goods. And then you have profit. And that's basically it. So that's the whole secret about it. Well, of course, it's not that easy to do. Actually, develop an awesome game is quite hard to do. And then you have to get users somehow. And also to sell virtual goods is not that easy. So what you have to do for that is you have to do kind of marketing and also kind of CRM, so customer relationship management. And my talk will focus on a use case in that direction. So it's about CRM, and especially it's about those interstitials. And I will show you such an interstitial on this slide. So an interstitial for InnoGames is basically nothing but an in-game pop-up message. So imagine you play a game, and then this pop-up appears, and you can get 10% bonus if you buy crowns in this example. And this is basically something that we're doing batch-wise. That means every night we are selecting a bunch of users based on some requirements, and then we are sending out those campaigns, basically. Now, the whole idea that we have now for this project that I want to show you today, I want to tell you a little story for it. So this is Bob. And Bob plays Forge of Empires, obviously. That's the game that InnoGames has implemented. So if you'd like to give it a try, just feel free. Or if the talk is boring or something, please play Forge of Empires at least. OK, so Bob plays Forge of Empires, and now he gets such an interstitial message. But he doesn't know what to do with it. So it's not very attractive for him. It's just getting him 10% free diamonds now. And yeah, he doesn't know what to do with it, so he clicks it away. And then he continues playing the game. And then all of a sudden, he loses 3 battles in a row. So he is stuck in the game, he doesn't know what to do, and he's very frustrated. Now, after a few seconds later, he now gets this interstitial, and it's an interstitial that is tailored for him. So that means it's exactly what he needs in this moment. He needs 4 battle tanks to win this battle, obviously. So that's what's missing in his army composition, basically. And yeah, he gets this interstitial, he is very happy. He accepts the offer, and yeah, he's happy. We have a new paying user, basically, and we prevented a churn. So that means he continues to play our game, and he's happy with it. And this is the motivation behind the project Real-Time CRM, and that's what I want to show you today. And basically what it is, it's individualized marketing based on user behavior in real time. And what do you need for that? So first of all, you need data, of course. And at InnoGames, we are mainly tracking so-called events, which basically show the user interaction. That means when you play our game, you interact with the game, and we record those interactions as events. So for example, this is Forge of Empires again. And if you now, for example, build a building, then you get a build event. If you do a fight, then you get a fight event, and so on and so forth. So it's fairly simple, but you can imagine it's quite a lot of data that you can generate that way. And actually, talking about buzzwords and numbers, I brought you a number. That's a big number. It's 500 million. And this is actually the number of events that we collect per day. So that's the amount of data that we have. Actually, that's, of course, compared to some other bigger companies, it's not that much. But I think for our business and our company size, it's already quite a bit. So that's what we have to deal with, basically. And to collect this data and to process the data, we build up kind of a data infrastructure at InnoGames. So that's what my team is doing, basically. And it looks like this. So this is basically the data processing infrastructure that InnoGames has. And, well, it's fairly simple. But imagine this is all in a distributed world, so it's very simplified, that picture. But let me guide you through it from the left to the right, basically. So on the left side, as you can see, we have games and other systems. They are sending events to a gateway, which is the entry point for the whole system. And then it continues to push those messages into a message bus, and that's where the real-time processing happens. For the real-time processing, we also have kind of a persistence layer that is optimized for write and read performance. So this is our production storage. And then in the end, we have Hadoop, of course, for distributed storage and distributed processing. And we are mainly doing batch processing in that area. In the end, you can see that we have different systems that are connected to our Hadoop cluster. So we have a business intelligence system based on SQL Server that is fetching the data from Hadoop. We also have a great analytics department, so with data scientists, and they are working with the data day by day. And of course, we have other systems such as Power BI, for example, or Tableau. And talking about timings, as you can see on the top, as soon as an event gets generated in the game, it takes about 3 to 5 seconds until it arrives at the gateway. This is because we have a special process that decouples the sending of the event from the game itself. So it makes it very safe. If the whole system explodes, the game will still work without any problems. So we're talking about seconds in that area. After it arrives at the gateway, we are talking about milliseconds. So after that, we can process all those events within milliseconds. And then, of course, on the batch side, we are talking about hours because we are processing the last hour, the last month, whatever. So that's basically the whole data infrastructure that we have. And when we talk about the left side, we're talking about the data pipeline at InnoGames, and the right side for us is basically the data platform. And since we're on the Berlin Buzzwords, I have brought you some buzzwords. Basically, those are the technologies that we use for it. So on the client side, we have a client implemented with the Go language. It's quite cool and quite handy. And for the gateway, we used Java, basically, and with the Drop Wizard framework, which is a framework to implement REST APIs. It's very simple. Then, of course, we use Kafka, like everyone. And then for the near or real-time processing, we're using Apache Storm, Apache Cassandra for the production storage. And on the Hadoop side, we are basically using most of the stuff that the Hadoop infrastructure offers us, like Hive and Spark and different other technologies. So that's basically how it looks like. And when we are now talking about this real-time CRM project that I showed you in the beginning, it's happening in the data pipeline part. So I focus on that part right now. And to give you an idea of what happens there, it's fairly simple, basically. So you have 5 simple steps that are happening within this real-time CRM process. First of all, we have events that get sent to the gateway. The gateway is then pushing it to the message bus, and then the events get processed event by event, so as a stream. And then 2 things happen, basically. First of all, we update a player profile with those events in Cassandra. That means it's basically some kind of storage that can tell you everything about a player in real time. So, of course, we do not record everything, so every single event, but those events that are interesting for us. And then after that, we trigger campaign based on the current player profile and the incoming event. And that's basically it. So that's the whole magic behind the real-time CRM project. And the key technologies for that are basically Kafka, Storm, and Cassandra in our case. And I want to focus on how we use those technologies for that project right now. So starting with Kafka, I think most of you know Kafka or use it in production. So who's using it in production? Just quick hands up. So, okay, that looks good. So I can make it very fast. It's very good. Okay, so basically, you know that in Kafka you have brokers, which is basically a Kafka cluster. You have several producers and several consumers. And the cool thing about it is that you can write once, but read it many times as often as you want. And internally, you know that as well, I'm pretty sure. You have brokers, you have partitions. So in this example, we have a topic called logs. It has 2 partitions and replication factor of 2. And it's spread it around the cluster in those 2 brokers. So that's basically the idea behind it. But I think more interesting is how does it look at InnoGames. So at InnoGames, we have 5 nodes, 5 Kafka nodes with 8 cores, 64 gig memory, and 1.8 terabyte disk space each. And those are basically the settings. You can see them on the right. We are using Kafka 0822, so we have to update soon because there are cool new features that we want to use, actually. And this is how it basically basically looks like at InnoGames. And talking about the topics at InnoGames, we have currently just 3 topics. So it's kind of the first project that we ever did with this pipeline. So that's why we only have 3 topics for now. But let me talk about those topics. So I start from the bottom and then I go to the top, actually. So I start with the raw topic. That's a topic where we actually store the events. So it's our main topic for everything. Then we have a maintenance topic. It's clear what it is. So we store maintenance information, all the components in the pipeline that you've seen, send some information to this topic, and you can just check everything on the maintenance topic. And then we have the CRM trigger topic, which is quite interesting because we actually use Kafka as a message bus. Means if we want to communicate that this interstitial should be shown to a player, we write it back to Kafka, and then another system is reading it from Kafka and actually is performing this interstitial magic, basically. And you can see in the bottom, our raw partition has, our raw topic has 16 partitions, replication factor of 2, and it stores, I think, 7 days of data, no, 4 days of data. So if anything fails over the weekend, we should be safe, hopefully. That's about Kafka. Now it gets a bit more interesting because we chose Storm for the stream processing part, and actually that's where all the logic happens. So I think many of you know Storm already. It's kind of the old school distributed real-time computation system, and still I want to show you the basic features or components of Storm, or the idea behind of Storm. So Storm has spouts, which are basically the sources of data streams. Storm has bolts. Within bolts, you do the actual processing. You can also generate new data streams out of those bolts. And in the end, you have a topology, which is just a composition of those components. So very, very simple, basically. And to show it to you by an example, this, for example, is a temperature alerting topology. So very simple. On the left side, you see a temperature bolt that reads the current temperature from a sensor. And every few milliseconds, it's emitting those values to the next bolt, which is the filter bolt. And the filter bolt is actually checking if the temperature value is more than a specific threshold. And if that happens, it will send another message to the next bolt, which is then the warn bolt. And it will just, I don't know, write an email or raise an alarm or something like that. So that's a really simple example for Storm topology. And if you look at the implementation, it's also not that complicated. So this will be the filter bolt, basically. You can see it on the right side that you have a prepare method where you can prepare your bolt. You have an execute method that gets the actual tuple. So that's where all your logic goes. And then you have a declare output fields method where you can declare what kind of output your bolt is generating. So that's basically it. So extremely simple, but also very low level. Storm also has a high level API called Trident, but that's not part of this talk. You can look it up if you like. But what we did with Storm is this. So this is the CRM topology, which is the main processor for the whole real-time CRM stuff. So let me go through it step by step. We have the Kafka spout that's reading stuff from Kafka, obviously. It's reading the raw topic, the events. Then we have a validation bolt because, like every big data project, data quality is always an issue. So we have schemas, and we are validating our events with those schemas, but that's different story. Just what is important is we only want valid events, of course, and those valid events get then partitioned by player. And we do this using a player partitioner bolt, and that's a very important component because if you work in a distributed system and you don't think about how to partition your data, you can get really easy very much in trouble. Because in this example, imagine you have much more instances than just one of those CRM bolt. And now the question is, if you have multiple events, how get they distributed to those instances of the CRM bolt? And by default, Storm is doing this randomly, but if you now want to have the events in a specific order for a player, you can get in trouble. That's why we have a player partitioner bolt. Actually very simple, but extremely important. So think about partitioning and stream processing. And the CRM bolt is something that I will show you in a bit. So just imagine that's where the magic happens. And then, as I already told you before, we are writing the information that an interstitial has to be triggered back to Kafka so that another system can read it and actually perform this action. Right. Okay. So this is a CRM bolt. Let me drink a bit of water. Okay. So this is the CRM bolt. This is where all the logic happens. And this is actually quite cool because it's very simple, but also very powerful. It's doing just two things, basically. First of all, it gets an event, of course. And then you have every event has a type. Like you've seen in the beginning, there's a fight event, for example. And for each event type, you can define handlers, update handlers or campaign handlers, or both, if you like. An update handler is basically just updating the player profile. So it's doing some updates in Cassandra. The campaign handler is then actually triggering those campaigns by using the event that's currently incoming and also using the current player profile. So by those two informations, it will trigger a campaign event eventually. And now the interesting part is that those handlers are actually defined in JavaScript, and we are using the Nashorn JavaScript engine, which is part of Java 8. And it's quite cool and handy, so we build a fancy class that we just use to call this JavaScript engine, and then in the end you have the updater and campaign handlers defined in JavaScript, and that's quite cool. So actually what Storm is doing for us, it's applying the JavaScript snippets that we have to each and every event. And those JavaScript snippets are basically containing the whole logic that we want to apply. So if you look in the example on the top, this one is counting the login events. So you can apply a filter. I only want to do it for login events, and then you can actually perform some actions with the framework object that we provided to this script, basically. So that's how we define the logic. And the cool thing about it is you can actually change the logic at runtime. So you don't have to redeploy the topology. You just let it run. You integrate new JavaScript, and so you can change the behavior of the whole system at runtime, which is quite cool. Okay, so that's basically how we do it in Storm. And talking about Storm, I also wanted to talk a bit about alternatives. We use Storm because of historical reasons. So it was the first thing that we tried out. It worked for us, and so we got stuck with it. But it's fine. I mean, it has some drawbacks, but if you look at the latest versions, they actually improved a lot. So in November 2015, Storm 0.10 was released, and it had some cool features, like, for example, Flux, which is a declarative language to define topologies. So before that, it was really like you had to write a lot of glue code to define a topology, a lot of Java code that is, I don't know, it's very hard to test, and it's not very developer-friendly, actually. But with Flux, you have just a YAML description of your topology. You have property files, you put it together, and then you can deploy your topology. So it's quite cool. Beside that, you have rolling upgrades, you have some security features, and you have improved logging. So that's already a really, really good milestone. And then this year, in April, actually, when the Hadoop Summit was happening in Dublin, they released version 1.0, which is quite cool because it has a lot of performance improvements. So on the website, it says like 16 times faster, at least 3 times faster. So of course, it depends on your use case. But they actually worked on the performance, which is quite good. Then you have Pacemaker, which is a Zookeeper replacement for worker heartbeats, also very cool and useful. And as you can see on the bottom, they also thought about how to store state for the different components. So now you have a distributed cache, and you also have state management. So it has quite cool features, and even more features, like back pressure, resource away scheduler. It now has a native windowing API, and you have improved debugging and profiling, especially in the Storm UI, if you ever seen that. So you can have tuple sampling and stuff like that. So they improved a lot. So Storm is not dead or something, so you can still use it for those projects, even though there are a lot of alternatives, as we have seen on the conference. And yeah, you have to choose wisely. And for example, you have Kafka streams, you have Spark streaming, and you have Flink. So those are the things that are actually quite hot right now. And yeah, you have to think about those alternatives. For our use case, Storm was completely fine because we decoupled the whole logic in this JavaScript snippet, so we could do it with any of those systems. Of course, we require low latency, and that's why we also chose Storm, basically. And to give you some more input, you should check out those presentations, actually. The first two were happening yesterday about Kafka streams and Apache Flink. And the last one was to talk about the new Storm version at the Hadoop Summit. So if you are in the state where you have to choose a stream processing system, just have a look at those presentations. They're very good and very informative about that. Okay. The next component in this whole infrastructure that we used for the real-time CRM stuff was Cassandra. And like I said, we use it to store basically a player profile. So talking about Cassandra, just quick question. Who of you is using Cassandra in production? Does anyone use it? OK, that's quite a lot, actually. Yeah, I will make it short. So basically, Cassandra is a project developed at Facebook. It's open source, and it's based on DynamoDB by Amazon and Bigtable by Google. And for this presentation, I thought, how can I explain Cassandra with just one slide, basically? And I think that's quite accurate. It's not perfect, but I think it describes it very well. So if you think about Cassandra and the data model behind Cassandra, just think about it as a sorted map that has a row key, and then again a sorted map with key value pairs. I think that's basically the idea behind Cassandra. And you can see, based on the row key, you have a hash value, and then with consistent hashing, the data gets distributed around the cluster, and you have also data replication. So I think that's basically the idea behind Cassandra, and it's also explaining it very well. So that's basically Cassandra. And going more in detail about the data model in Cassandra, on the left side, you have an example for a bad data model. On the right side, you have an example for a good data model. So what you should not do is you should not have something like a row key based on the hour or the day, and then timestamp payload as the rows, as the columns, sorry. Because the issue that you have is what you want to spread the data evenly across the cluster. And if you have the hour, for example, as a row key, you have the issue that the queries of the same hour will always go to the same node, so you don't have parallelization at all. So it's very bad to do it like this. On the other hand, if you use a timestamp, for example, so for time series data, you might have the issue that you have two different payloads with the same timestamp and you overwrite your data. So a good model would be if you choose something that spreads the data evenly across the cluster, like a combination of the hour or the day together with an ID. For us, it's the player ID, for example, and you have to use the time UUID instead of just the timestamp. So that would be a good model. And basically, as you can see on this slide, your goals should really be, you should spread the data evenly across the cluster, of course. You should minimize the number of partitions to read. Means if you want to know something, it's good to only read as few partitions as possible, of course. And what is also very useful is if you start thinking about your queries and then start thinking about your data model when working with Cassandra. Well, and that's what we came up with for our data model for the player profile. So basically, what we did there was we have the unique player ID, which is a unique identifier for the player. We have the day, and that's basically our row key. So by this row key, we distribute the data across our cluster. And then for the column keys, we have time UUIDs, like I mentioned before. And then we just store the type of the event and the event itself. And then we can use it in our application and can read the data from it. So that's basically how that works. And yeah, the issue with it is you are very fast if you want to know something about a player on a specific day. For example, if you think back to Bob, yeah, Bob lost 3 fights in a row. If you want to know that, it's very simple. You just query Bob by its player ID and also for the specific day, and then you know, okay, he was losing 3 fights already that day. Now, the issue is if you want to know all the players that already lost 3 fights, so you turn it around and you want to do an analytical query on that data, then you might have an issue because you have to scan all the row keys, and that might take some time. And that's why we also threw in a pinch of Spark. So we use Spark for analytical queries in that case. And I'm sure most of you know Spark already. So again, the question, who's using Spark in production? I think a lot of you, yes. That's what I thought. So again, Spark is basically a general purpose cluster computation system. That means that you can use it for any purpose, and it can run standalone, it can run on Mesos, it can run on Yarn, so it's very flexible in its environment. You have different data source APIs, so you can use data from Hadoop, from Cassandra, Hive, HBase, whatever you like. And then you have, for example, the data frame API. Right now there's also the data set API, which is even, it's even on a higher level, basically. And with this data frame API, you can then use different libraries and different languages to work with your data. After that, Spark is generating a DAG out of your application code and will process the data on the cluster, basically. And that's what Spark is doing. Now, what we did with it is that we actually installed a Spark cluster alongside our Cassandra cluster to solve this issue. And this is quite cool because there's actually a Spark Cassandra connector by DataStax that we use together with the fact that we have data locality. And based on that, we can do very fast analytical queries on Cassandra data. And actually, this solved the issue that we are not able to find out how many players lost 3 fights already. Beside that, we tried another project called the Spark Job Server. I don't know if you know that, but it's quite cool. It offers you a REST API that is able to run Spark logic on a Spark cluster. And yeah, you can interact with it using a REST API. And the cool fact about it is that it's managing context objects. So in this case, in this example, as you can see, we are caching a Cassandra table. So we're using Cassandra SQL context, and we are caching a Cassandra table if it's not cached already. So in the bottom part right here, the first time you run the code, this will take quite a while. But the second time you run the code, it will be very fast. And if you have different analytical queries than that on the data, they will also be fast because the data is cached already. Of course, you have to clear the cache from time to time, like how you like it, for example, every hour. So you have to recache it. But using that Spark job server is quite powerful to do those analytical queries. This is actually something that we don't use in production right now. It's just playing around with it, and because we have to find a solution how to run those analytical queries. And for now, it works quite good. So if you are interested in that, give it a try and give us feedback if it works for you, actually. OK, so now I want to put all that stuff together again. So I've shown you several components of this real-time CRM project that we run at InnoGames, and it's all happening within this data infrastructure, basically on the left side, so on the data pipeline. And there are some takeaways that we learned from that. So first of all, Kafka is quite awesome. I think we agree with that because it works really well for us. Before we used Kafka, we used Kestrel, and we had several issues with it. And then we switched to Kafka, and now everything is fine. And actually, the more we use it, as it's desired to be, so as a message bus, the better it gets. So it's quite cool. Storm, actually, it works quite well for us. So it makes it easy to actually write those real-time computation applications. But we had performance issues. And it was also in the beginning very hard to define topologies because you had so much glue code that was really hard to test, and it was not developer-friendly. But like I've shown you, those disadvantages were addressed and also resolved partially in the newest versions 0.10 and on 1.0. And yeah, so that's about Storm. Last but not least, reacting to user behavior is quite powerful. So I cannot give you any numbers on uplifts, how much uplift it generates, because it's just running on some test markets right now, but it looks already quite promising. And if you think about it, it's quite powerful because it's basically the next step to do marketing or CRM based on the user behavior in real time. Now, the issue is with that, it's not only a challenge for the developers, it's also a challenge for the game designers in our case. For example, imagine you have some bug in this JavaScript, some wrong definition, and all of a sudden all the players will get those 4 battle tanks for free. And all of a sudden your complete game is ruined and the whole game balance is broken. So it's quite dangerous to react in real time to the user behavior if you not think enough about it before. So it's also a challenge for the game designers. And combining Storm actually with Storm was a great idea. It was very fun to do. We didn't have any performance issues so far, and it's quite cool because you can define the whole logic in JavaScript, which is quite a good feeling. And it can be changed at runtime, of course. That being said, the whole project was very fun to do, and we used a lot of those technologies. Actually, the next step for us would be to think more about the analytical queries on Cassandra. Also, maybe we think about switching from Storm to Flink or just give it a try maybe. And yeah, and then we have, of course, to bring it from the test markets to the production markets to see what kind of uplift it can generate for us. So that was actually quite fast, and that was the project already. So I hope I could give you some small insights about what to do, what you can do with those technologies, some practical use case. And if you have any questions, feel free to ask. So thank you very much.
Thank you very much, Volker. Questions? We have 10 minutes to take the questions. Any questions?
I think over there.
I see a hand here and one there, right?
There, okay.
Yeah. I'm curious if how it has, if it has worked well for you to run the Spark on top of Cassandra, and what the largest RDD sizes that you process are.
Sorry, again the question?
I'm curious if you had any problems running Spark on top of Cassandra, and especially since it's part of the critical pipeline for the real-time processing as well.
Actually, no, so far we didn't have any issues, but I have to say that the use case with Spark or Cassandra that we tried out is very small. So it's really, currently we are not using all events to be stored in the player profile. So it fits in memory. It's fine for what I can say right now. But yeah, it might be, it can be hard in the when you have too much data that doesn't fit into memory. But for now it works quite well. And it's also just, we just gave it a try. It's just testing how to do those analytical queries. Actually, it's based on a blog post from DataStax, so they have a presentation about it. You can Google for it, and you get more details about it. But for us, it works so far, so that's what I can tell you.
Thank you. Any more questions?
So, really simple question. If you already have Storm cluster,
yes,
or like Flink, why not to do some analytics already on that step? Why, like, all this chain? You can pre-compute something.
So the question is, why are we doing the analytics not already in Storm, you mean? That's why, basically what we build up is, I can go a few slides back, so this one maybe. So the production storage in that case, or the whole data pipeline, doesn't know the whole history of the player. So that's one issue for us. And we keep the whole history in Hadoop, and that's why we need some data from Hadoop as well. So that's why we do it later on the analytics, basically for now. Of course, you can think of doing more analytics already on the left side. Actually, we are thinking about it. But for us, the issue is that we have a lot of data, and it's all within Hadoop currently. That's the issue. So. Yeah. But good point, yes.
Any more questions? Super.
How big is your Cassandra cluster?
Currently, it's just 8 nodes. So it's quite big nodes, but yeah, 8 nodes currently.
All right. And I saw you had, what, 16 partitions in Kafka, like per topic?
Yeah.
How come you chose 16?
In this case, 16, good question. It worked for us. So I could go back to that slide. Actually, we chose 16 partitions because that worked for us quite well. So it was trying out. It's not by the book, basically, but that worked for us quite well. So it's just by benchmarking.
No, because I was thinking, you might have want to use more, because what you had 5 nodes, 6 nodes with 5 each
Kafka nodes,
8 cores.
Yeah, 8 cores each.
That makes, what, 40 cores in total? If you then have 16 partitions, then it seems that you would have a bottleneck on the partition side at some point, maybe.
Yeah, at some point. It might be true, yes. Good point. Okay.
Thank you.
Any other questions?
Okay. Thank you so much, Volker. That was a neat presentation. Thanks a ton.
Thank you.